Okay, folks, let's continue. Another very boring and technical lecture today, but it is very important for your second year when quantum mechanics strikes you, because that subject is all built on differentiation operators. The linear and angular momentum in quantum theory are built out of differentiation operations, and it is important for us today to go through your knowledge that you already have from school in some greater depth. That is, I will explain to you where exactly derivatives are coming from in modern mathematics. All those rules that you have seen at school as to how to differentiate, we will today actually derive from the ground up. And then I will introduce the notation that quantum theory uses for differentiation operators, and explain that in a sense differentiation is an object that is separate from the function that's being differentiated, which is an instruction of a sort, an abstract. Okay, but for now we begin with just a deeper go through what it means to be a derivative, and the first item is the definition of the derivative. As it is understood by modern mathematics. Well, as you know, derivative is the rate of change in a particular function. If the function depends on time, that's simply the rate with time, like coordinate and velocity relationship. Or if the function is the slope of the ground, for example, if the function is the altitude, then the derivative is the slope of the ground. What it is ultimately from physical perspective is if we take the function at some point x and we shift that point a little bit by delta x and we calculate the difference between the function at the slightly shifted point and the point in the original position and take it relative to the displacement that we have taken, then this is in some sense the measure of how steeply the function grows. If we go to some common chemistry like magnetic resonance spectroscopy, all of you will be doing NMR in due course. Second years have already done it, nuclear magnetic resonance, where the amplitude of radio frequency absorption of your sample will depend on the frequency at which you are irradiating. And a typical NMR signal looks like something like that. Grows and then decays. Let's now think about what a derivative of this thing would be. Well, since the derivative is the rate of growth and it started off flat, there was no growth, and so the derivative at some initial point in the frequency axis would be exactly zero. And then at some point that function begins to grow, so it accelerates and the derivative will become positive, but then it slows down again and eventually stops growing. And so at some point we will have a burst of acceleration and the thing will slow down and then hit zero at the point where it has turned around. And then of course it decelerates, and so the speed will be negative. Counterfeit here, and eventually it will return to zero because there's no change anymore here. So what we need to do in order to gauge the rate of change is to take the function at some point here and at some point here, look at this difference, right, so that's delta f, make the difference relative to how much displacement we have taken, so that's delta omega in that case. And of course, we'd like this measure to be strictly local. That is, because the function keeps changing all over the place, we'd ideally want these points to be as close together as possible, and so we put a limit in here. Limit of delta x going to zero. And that is the exact rigorous modern definition of a derivative. It is the limit of delta x going to zero of the change in the function when we displace an argument divided by the displacement of the argument. And you can see why I had spent so much time dragging you through limits, because these infinitesimal quantities and manipulating them are actually essential in the subsequent mathematics. Okay, now technically speaking, this formula, as we will now see, is sufficient to differentiate any function, however complicated. Let me give you an example. If we have something like what in your handout, a function of time, f of t, will be 5t squared minus 2t plus 8. Let us now differentiate it, not by the textbook rule, which would be trivial in this case, but let us differentiate it using this limit definition. So, we would want f of x plus delta x. The argument in this case is t, so this becomes f of t plus delta t. So 5t plus delta t squared minus 2t plus delta t plus 8. That is the function that has been displaced from the original time position by delta t. Then minus the function itself, so 5t squared plus 2t minus 8, all of it divided by delta t in the limit where delta t goes to 0. T is the limit of delta t to 0. Well, let's just open all the brackets. Limit delta t to 0 of 5t squared plus 10t delta t plus 5 delta t squared, then minus 2t minus 2 delta t plus 8, and minus the original function, minus 5t squared plus 2t minus 8 divided by delta t. Quite a few things will now cancel. Notice here plus 8 minus 8, that goes plus 2t minus 2t minus 5t squared plus 5t squared. Then I think that's it. And then a few things will cancel with the delta t, but let's just rewrite this one more time. So we have limit of delta t to 0 of 10t delta t plus 5 delta t squared, and then minus 2 delta t divided by delta t. Well, you can see delta t in the numerator and the denominator, so another instance of it cancels. Limit delta t to 0 of 10t minus 2, and then plus 5 delta t. The limit of that when delta t goes to 0, well, this just disappears, and so that's nt minus 2. And that you would notice is actually the textbook rule derivative of the original thing. If we do it by the rule, f prime of t, derivative of t squared is 2t, so a total of 10t minus 2. It is pretty clear that it is easier and faster to differentiate this by the rule, I've just done it in 5 seconds, than it is to drag along this enormous limit procedure. I have given you an example in the handout of an even more horrible case, which I will not write out explicitly, but I will simply illustrate to you, and then you would probably be able to tell at that point that it's not a good idea to write that all out, but I can just do it as a homework exercise. If you have a function f of x that contains, for example, a square root, root x plus 1. Any of you would be able to differentiate that straight away, or at least once you've reminded yourself how to do it by looking into a textbook. But the limit definition is again horrendous in this case. We would have f prime of x as a limit delta x going to 0 of the incremented function 2 minus x plus delta x plus 1 minus 2 plus root x plus 1 divided by delta x. And then we would have to multiply and divide this by the numerator where this is a plus to get rid of the roots, and then to simplify a horrendous quadratic expression and ultimately take the limit, all for the benefit of simply recovering the expressions that you already would have seen in the textbook. 1 over 2 plus 1, right? We all know how to differentiate powers, including fractional powers, but this is where those rules are coming from. So let us now, instead of focusing on calculating every possible derivative the silly way, let us use the silly way to prove everything that you already know very rigorously, like the product rule, the chain rule, the basic rules for linearity of those derivatives, and basically we need to rigorously prove all of the results that you have already seen. The reason we are doing this is that there are other aspects in chemical kinetics and thermodynamics where similar limits occur in ways that are unrelated to differentiation. So you will at some point see numerous approximations in real life chemistry, like the harmonic approximation for infrared spectroscopy, where similar things are done. When we come to integration, you will see that the definition of a definite integral is also in fact a limit, but not of something like that, or something completely different. And so we are here not only retracing the steps, which would not be particularly exciting, we are training you to think in this kind of way about infinitesimals, about taking their limits, and about building up rules for efficient calculation of properties that would otherwise have been too hard to calculate. Okay, so let us prove a few things. You all know the linearity property for the derivatives, that for example, if we have alpha of x plus beta g of x prime, that numbers alpha and beta can be taken out of the derivative, and that the derivative of a sum is a sum of derivatives, right? Let us now prove it. We have a limit of delta x going to 0 of this entire crocodile that has been incremented, so alpha of x plus delta x plus beta g of x plus delta x, where delta x is that infinitesimal increment which we will eventually put to 0, minus the original function, minus of x minus beta g of x divided by delta x. Let us now split it up, and let us now assume that the derivatives in question actually exist. That is, all the limits that we have obtained are not infinite. Under those circumstances, we have seen in the previous lectures that the limit of a sum is a sum of limits. So I will keep all the x under one limit and all the g's under another. So that will be a limit delta x going to 0 of alpha f x plus delta x minus alpha x divided by delta x plus an identical limit for g. Limit delta x to 0, beta g of x plus delta x minus beta of x divided by delta x. And this is permissible under our assumption that the individual limits exist. The next thing I need to do is to take alphas and betas out of limits, and again you have seen that we're allowed to do that because alpha and beta are just fine multiplies. So that will then be alpha times the limit of everything that contains f going to 0 plus beta, the limit to 0 of everything that contains g. But notice that these are actually exactly the same as our original definition of f prime and g prime, except for the alpha that we have now taken out. And so this is alpha f prime of x plus beta g prime of x. And this is, of course, the property you are already familiar with for derivatives, except nobody has ever proven it. Now, that property is in a sense trivial because with a bit of experience and a bit of good luck, you would actually be able to see such things straight away, right? Limit is linear, that's linearity. Why don't we just do it? Let me prove to you now a non-trivial that would require a bit of setting up and a bit of fiddling and a bit of preliminary thinking, and that is the proof of the product rule. And again, you have been taught at some point that f times g prime, where these are two functions, is f prime g plus g prime f. The standard usual product rule. Let us now prove this really rigorously from the ground up. In order to do that, I need to set up some preliminaries first. Let's take a look at our definition here. That's our f prime, and that's the limit. In the case where we have taken the limit, this relationship is exact. That is, when delta x is infinitesimally small. If we are not quite there, if it's not infinitesimally small, just really small, then that would not be an exact relationship, it would be an approximation that may be closer or further away from the truth, depending on how close or far delta x is to 0. So we could say that f prime of x would be equal to the expression without a limit, f x plus delta x minus f of x divided by delta x, approximately. Now, what does it mean to be approximate? There is some kind of correction term that we don't know. We will call it phi. It will be a function of x and delta x, and that is simply the difference between the expression where delta x was infinitesimally small, and it was the true derivative, and the expression where it is perhaps small but not terribly small. And then that's the correction. And of course, by definition, right, the limit of delta x going to 0 of phi of x delta x would be 0. It will have to vanish because our f here, that expression would actually become equal to f prime. And this phi is something. It depends on x and delta x clearly, but beyond that we simply don't know it. Let us also now multiply both sides of this by delta x. So now delta x appears there, so f prime of x delta x would be equal to f of x plus delta x minus f of x plus phi x delta x. And that's just the rewrite of this. What I will also do is I will put that over to the right-hand side, left-hand side, and I'll put that over to the right-hand side. And so ultimately we will obtain the expressions of the following kind. F of x plus delta x will be equal. Okay, so if that is here, and for example we shift everything else over there and then flip the whole thing around, when f of x moves here it changes sign, when phi moves there it changes sign, and that just remains unchanged. So that would be f of x plus f prime plus our, or rather now minus our little correction term. X delta x times delta x. And just check that I haven't lost any minuses. No, I haven't. So this is for now just obscure exercise in pushing symbols around, but you will see why this becomes necessary. And we will do exactly the same for g, and we will write exactly the same expression for g. G x delta x will be g of x plus g prime x delta x. And because g is a different function, it will have a different correction term. We will call it x delta x times delta x. Alright, that is preliminary, and this for now we simply need to note that this exists. Let us now move to the proof of the pudding itself. You have all seen Marvel's latest Joker, I believe, and try and do the product. We have f of x, g of x prime. By definition, that is the limit delta x going to 0 of f of x plus delta x, g of x plus delta x, the displaced object, which is this product, and so we just displace both arguments, minus of x, g of x divided by delta x. But look at what we've got here. We have already made the preparations. We know what f of x plus delta x and g of x plus delta x are. And what I will now do is simply plug them here. That will be the limit. And I now need to be parsimonious with my whiteboard because this is big. Limit delta x to 0 of that entire expression, so f of x plus delta prime of x delta x minus phi. I'll be skipping the arguments and phi for brevity. Delta x. Then we got g of x plus g prime of x delta x minus psi x minus f of x g x divided by delta x. Let's open the brackets. Limit delta x to 0 of f times g. Again, skipping the arguments to make it short. F times g prime delta x. F times psi delta x. And that's enough for f. So f prime delta x times g. F prime times g prime delta x squared. F prime sine delta x squared. Then the last term in here, g phi delta x. G prime phi delta x squared. And finally, phi psi delta x squared. Divided by delta x. And at the very end, not forgetting that minus g. And yes, I managed to fit it into half a board, which is a challenge for that thing usually. Let's see what cancels. Our fg with a minus here cancels fg with a plus here. Let's look around. We have delta x squared in here, and it will be divided by delta x, but I reminded you how quickly different functions fall off and rise in the lecture about the limits. Delta x squared falls faster than just delta x. And so when we take this out, it will be f prime g prime delta x would cancel, and so f prime g prime delta x. When delta x goes to 0, this would disappear. So that goes. The same applies to this. Not only we have delta x eventually multiplying that, we also have psi that, as per our little discussion there, phi and psi are corrections that must go to 0, and so that term, likewise, has to disappear. So that goes, because it becomes small. That goes for the same reason, because it becomes small. This is really, really, really small. Right? Psi is small, phi is small, and delta x is small. Fourth order kind of small. And then let's take a look at what else we've got here. Here, delta x will cancel, but we will have f psi. Psi goes to 0. Go on. And here, we will have delta x cancel, but phi goes to 0. That's gone. And after the dust has settled, and only the relevant terms have remained, we have limit delta x to 0 of f g prime delta x plus f prime g delta x divided by delta x, which is the limit delta x to 0 of delta x just plainly cancels in numerator and denominator, f prime g plus g prime. Delta x doesn't even occur, and so we can put it to whatever we want, including 0. So f prime g plus g prime, which is exactly what we wanted to prove. That is the product rule. So let me walk you again through the entire procedure, because you can see it contains an element of preparation. You need to know where you are going, and when you see proofs in textbooks, unfortunately, typically people just pull rabbits out of hats. They know where they're going, and they say, okay, let's make these preparations. It normally becomes clear why those preparations have been made in the course of the subsequent proof. Okay, we decided to prove this wondrous equation here. And in order to do that, because somebody across the history has made many unsuccessful attempts and eventually found an elegant way of proving it, we need to do a bit of preliminary philosophy. The philosophy consists in us noting that the definition of a derivative is a limit. However, if we don't go to the actual infinitesimal, don't go to the actual 0, but instead pick delta x that is small, but not outrageously small, then that expression would cease to be exact, but it would be an approximation of some kind. So this is our non-limited expression, and that's the difference between that expression and the right answer, and clearly the difference has to go to 0 as we put delta x to 0. And the same applies for g, but with a different correction function, which we had called psi. What I then did is I multiplied both sides by delta x, there, and rewrote the expression like this. And then I really wanted that to be solved for f of x plus delta x, because I kind of suspected that we would be using it later. And so, whichever way you play it, when you rearrange the terms, you get this. We have the expression for f and g implemented through the original g on the tangent line. In fact, some of you will recognize that, and then some correction term that accounts for the fact that we are not yet in the limit. Okay, then I proceeded to the substance of the proof. and said, okay, the definition of a derivative is we must increment whatever's in the brackets. Here it is, increment. Subtract out the original unchanged function, there it is. Divide the result by delta x and take the limit. Now, without our preparation work, we would have been stuck because we don't know what f is, we don't know what g is, we don't know how to open this up, and it would have been difficult. But we have done our preparations. And so I'm plugging that f of x plus delta x right here, and then g of x plus delta x right there, and I'm rewriting that. Through their writing, I've been skipping the brackets, right? So f of x, well, we know that f is of x, why don't we just call it x? And that kind of saves the space, otherwise it would have extended all the way to the solid cell. Okay, that's the expression substituted in, and then carefully and painfully opened the brackets and wrote all of that out, and then started thinking about what cancels and why. Fg plus Fg minus cancels obviously. Then if we look at, for example, that this is f prime times psi times delta x squared. F prime is finite by assumption, it's a number, it's the rate of growth. So it's just a number at any particular point, x. Psi is that correction that's supposed to go to 0, and then delta x squared divided by delta x. Were we to simplify this by dividing delta x out, this would have been f prime psi delta x. In the limit, that's obviously 0. And so we can just drop it from the limit because it doesn't actually influence the eventual value. It's 0. The same applies to this, the same applies to that, and that. Each requires like a careful stare at it and a small amount of thought, and then we just cancel it because it doesn't influence your eventual limit. The terms that we couldn't do that to are this fg prime delta x and f prime g delta x, because they actually depend on the same power of delta x, and f and g are finite things. Okay, we kept them, and then we canceled delta x, and we realized that we've got this expression which no longer even depends on delta x, it goes to 0, wherever it wants to go, doesn't matter. So that is f prime g plus fg prime, and that's actually the problem. Okay, now, the bad news is that the quotient rule in Appendix A is even worse, and the chain rule is painful to even look at. Right? But they're in your appendices. Needless to say, I will not examine the appendices. Right? But I do expect you to understand what goes on here. So the kind of questions I would ask at the exams is, here's the horrible derivation, explain every step. But I will not ask you to reproduce the horrible derivations, because most of the time I don't remember that myself. Okay. More specifically, you have the list of 26 questions on Blackboard already posted, and one of those questions, we don't know which, will appear in your examination. So the best way to get prepared is to simply study the 26 questions, and then you're guaranteed 25% of the marks, because this is what it counts. This is a Russian style of the examination, where they just release 100 possible question sets, and if you've done all 100, you will pass the exam, but you already know mathematics. Interesting concept there. Anyway, let us now give a few demonstrations of how the derivatives are obtained from that famous table that you were asked to memorize at school. You all remember that the derivative of a constant is 0, and we can easily prove that. Alpha is a constant, then alpha prime is a limit over x going to 0 of, well, alpha doesn't actually depend on x, and so it is alpha minus alpha divided by delta x. And here we have an interesting piece of philosophy. Alpha minus alpha is identically 0, as in like proper hard to 0. Whereas delta x is asymptotically 0. It only approaches. It's that 0 is stronger than that 0, and so this limit is 0. So the identical 0 is cooler 0 than that 0 that only needs to be approached. Now I can see sort of my philosophy friends smiling, and certainly this is what we do in mathematics. This is life. Right? And so the derivative of a constant is 0. Now, a slightly more interesting topic is the derivative of the powers. Let me just go through exactly how the books have done. We can do the derivative of x literally. X prime is limit delta x to 0 of x plus delta x minus x divided by delta x. X and x cancels, delta x over delta x is 1, which leads to the conclusions that you already know about what the derivative of x is. What is interesting, however, is what is the derivative of x to the power m. Let us split this into x to the power 1 and x to the power n minus 1. We are allowed to do it because that's the same thing. And then we will apply the product rule that we have just proved. So this will be the derivative of the first term in the product, which is 1, times the second term, x and minus 1, plus the first term times the derivative of the second term, and minus 1 prime. Remember those implicitly defined, recursively defined sequences that I introduced in the very first lecture. This is one of them. This is the next derivative, the derivative of x to the m, expressed via derivatives of the previous term, derivative of x to the power n minus 1. Well, let's try x squared. X squared will be n is equal to 2, so we will have x to the power 1 plus x times x to the power 1 prime, which is 1, so x plus x is 2x. And for x cubed, the process is called induction, by the way, in mathematics. N is 3, so this is x squared plus x times the derivative of x squared, 2x. X squared plus 2x squared, 3x squared. And by this time, you can see the pattern. Dot x to the power n prime is n x n minus 1. And this is how that expression was obtained in your great big table of derivatives that you are supposed to memorize. And that big table, it's not actually terribly big, is in your handout. I will insist that you memorize the content of that table if you haven't already. Differentiation is a fundamental operation in physical sciences. As a scientist, or as a human, you are supposed to be able to breathe, to be able to walk, and to be able to differentiate. This is absolutely essential in your life. And so just learn to do that as fast and as soon as you can. What remains is to introduce a few alternative notations for derivatives that you will encounter when quantum mechanics strikes you in your second year. And there are two things that one must notice. First, that there's an abundance of notation. You can call it g prime of x. You can call it dg by dx. The reason for this notation, this was introduced by Leibniz, is that he considers d to be the limit of the delta. Right, so the limit of delta. So the increment that is already infinitesimal. It's strictly speaking called differential, and that will be introduced a couple of lectures from now, but that's the other way of writing that down, or equivalently d by dx of g of x. And it is this notation that you will be seeing a lot in quantum mechanics. Notice here that we have split the derivative into that which is being differentiated and the instruction to differentiate. It says, here's the function, go forth and differentiate. So that is called an operator. In this case, it's a differentiation operator. Operators have a life of their own. You can add and subtract them, for example. So if we define something like this, alpha d by dx plus beta d by dt. When this is applied to the function of maybe two variables, you sometimes use curly d's. In fact, it would be preferred to use curly d's in here, the so-called partial derivatives. So it gets f of x and t, and that would be alpha d by dx f of x t plus beta d by dt. All subsequent notation will be using curly d's. I'll explain to you why that's the case in the next lecture, actually. But you can see that you can add two instructions together on the understanding that you can simply just open the brackets and enter into the usual derivatives. You can subtract operators, you can take the inverse of operators. In that case, this would be integration, and so on. And what is important is that a lot of this pertains to physics. In particular, one of the most common operators in physics is momentum with respect to x. This is minus pi h d by dx, partial derivative with respect to x. And you can see the little hat in here. It indicates that an object is in fact an operator rather than a variable or a function. A hat indicates an instruction to perform some transformation. That's momentum. If you're looking at, for example, reactor modeling in industrial chemistry, you will sooner or later come across a diffusion operator. That is called d. Again, this will be d2 x squared. So second derivative operator that whenever something occurs in front of it, simply differentiates it twice. And plenty of other things. There will be inversion operators, integration operators, differentiation operators, permutation operators, translation operators, you name it. There's plenty of that stuff. All of this occurs in the theory of partial differential equations, in quantum mechanics, in thermodynamics, in special relativity, and such like. So when you encounter these things, don't be surprised to see a derivative that's apparently hanging in the air. That is simply an instruction to differentiate whatever it is that occurs in front. Okay, now I still have like 100 seconds, so let me just differentiate something horribly complicated and illustrate to you all the rules that we have done here. So I'll differentiate this. The cosine x log x divided by x squared. Fine. What have we got here? Well, the outer thing is a ratio, so we've got the quotient rule where it's numerator prime of x prime times the denominator minus denominator prime of x times the numerator divided by denominator squared. Notice that I've left the derivative unopened because it kind of looks complicated, and so I decided to just leave it be for now. But I will deal with it in the next step. So what we have here is the derivative of a cosine is minus sine times log x. So that's the first term in the product rule. Second term in the product rule is cosine times the derivative of z. The derivative of a log is 1 over x. So plus cosine x over x. All of that is still times x squared minus 2x cosine x log x divided by x to the fourth. And you may or may not want to open up and simplify that. If the job was to differentiate, at this point you get full marks in the examination because you differentiate. Cosmetic simplifications we do not insist on, so long as the answer is in principle correct. So here you see a fraction and then a product. The outer function is a fraction. Use the quotient rule first. There will be some derivatives in the numerator. Then this is a product rule. Open it up. Derivative of the cos, derivative of the log. Open up, simplify, return. It is impossible to master this without a lot of practice. That is, your class will focus on differentiating horrendous functions until this becomes completely automatic. You should be able to think about whether, and your hand should be just doing that for you. It is absolutely essential that you learn that, mathematical competition with these things. Any questions?